Okay, wow. All right. So basically, we did everything else. Now we're going into percent yield. Percent yield is very similar to stoichiometry, except it has one last step. Ooh, sorry, I've been getting contractions lately. A student adds 200 grams of C7H6O3 to an excess C4H6O3. This produces C9H8O4 and C2H4O2. Calculate the percent yield if 231 grams of aspirin is produced in an experiment. Okay, so they're saying we have 200 grams of this. Okay, in the experiment, we produced 231 grams of that. Okay, so first of all, they're saying we have 200 grams of this thing right here, C7H6O3. In the experiment, so not in the actual equation, but when we do the experiment, in experiment, this means the actual yield is 231 grams of that. So now what do we want to find out? Well, we want to find out theoretically. So using stoichiometry, how many grams of this do we produce? So we know that in the experiment, we produced 231 grams. This looks like a 7. It doesn't look like a question mark. But theoretically, if we were to do the stoichiometric calculations, how many grams of this would we produce? Okay, so first of all, we have 200 grams of C7H6O3. Okay, and we're going to do the steps that we've done before, right? We're going to go from mass to mole, mole to mole, mole to mass. We've done these steps before. We did them last week. Again, mass to mole, mole to mole, mole to mass. So we're going to have 1 mole at the bottom, 1 mole at the top, sorry, because that's what we want to get. We want to find out that, and we want to know the molar mass of C7H6O3. And just for time purposes, because we don't have too much time because of the assembly, I'm going to tell you these real quick. So C is in C7, so it's 12.01 times 7. H6 is 1.01 times 6. O3 is 16 times 3. Okay, so 16 times 3 I know for sure is 48. 12.01 times 7 is 84.07. And then 1.01 times 6, that's easy, that's 6.06. You add all these together, and you get 138.13. grams. And by the way, this is balanced. I just wanted to let you guys know. Okay. Now we go from mole to mole. Remember, what you want to get rid of is always at the bottom. We don't want to use C7H6O3 anymore. We now want, which is the actual, where the actual yield we got, which is C9H8O4. All right, and since they are balanced and we didn't use any coefficients, it's a 1-to-1 mole ratio. We keep going, and now we want the mass of that C9H8O4. So because we want to get rid of moles, 1 mole of C9H8O4 is going to go at the bottom, sorry, and then the mass in grams of C9H8O4 is going to go at the top. So again, C9, we said C is 12.01. We want to do that times 9. H is 1.01. We want to do that times 8. And then O is 16 times 4. Okay, so 16 times 4, 64. 1.01 times 8 is 8.08. 12.01 times 9 is 108.09. So we do 108.09 plus 8.08 plus 64. We get 180.17. okay? And that gets rid of that moles of C9H8. And now we do the math. So we do 200 times 1 divided by 138.13 times 1 divided by 1. Oh, sorry. Hold on, give me a second. I mispressed, okay? And then times 180.17 divided by 1. I got 260.87. And that's grams of C9H8O4. So theoretically, my theoretical yield now, I know is 260.87 grams. Okay, so like I said, it's very similar to stoichiometry. So we do the mass to mass first, and then here, then what we do is we have to take, we need to do the percent yield equation. And by the way, you are going to get this equation on the test. So you'll have it, you don't have to memorize it. It's always actual yield over percent, over theoretical yield. Times 100. Oh, 100, not 1,000. Okay. So what you're doing here is we need to know. So we have 231 at the top. Then we have 260.87 times 100. Divided by 260.87 times 100. I got 88.5%. Because it's a percent yield. Are there any questions? Okay. There's another problem there. I don't want to do it because I'd rather you guys do it on by yourselves. It's very similar to this. Again, I'm going to help you just right now with it to set it up so you guys know. So it says calculate the percentage yield. If you have 550 grams of Tulane, meaning you have 500 grams of this. And then in the experiment, when you do the actual experiment, you get 305 grams of this. So in the experiment, this is the experimental, or this is the actual yield. Sorry, let me do that again. In experiment, meaning actual yield, you get 550 grams of that. They want you to figure out the same thing. They want you to do the theoretical yield. So stoichiometry, to see how many grams of this do you get, and then you do the percent yield. I'm going to tell you right now, there is a problem like this on the test. So please, please make sure you try number 2. Again, mass to mass, just mimic what we did at the top. Mass to mass. Once you have that, that's your theoretical yield. That's the number that goes at the bottom. Your actual yield goes at the top. And then you do the, you guys do the percent yield. Are there any questions on percent yield?
No.
No. Okay. Remember, this is recorded. So you guys will be able to go back to watch this. Okay. So let me go into electron configurations then. Okay. So electron configurations, remember there's 2 types, that the main ones that we were tested on. Regular electron configurations and then noble gas configurations. We're going to do both. And then on, I'm most likely, guys, I don't know if I'll be here on Wednesday, just an FYI, because like I said, my contractions are getting more and more intense. I'm going to call my doctor after this. Most likely you're going to have a YouTube video for the last 2 parts, but we'll do electron configurations today. So it says, give the electron configuration for Se minus 2. Oh my God. Okay. Whew. Oh, sorry. I just have to breathe. Se minus 2. So Se, we have to find Se here. That's selenium right here. Selenium, remember, we need the atomic number. We want the atomic number, the number at the top, that's 34. So selenium, that means that if it has an atomic number, so remember the two equations that we want is atomic number is the number of protons. Okay, so if selenium's 34, that means it has 34 protons. Then how good does that do us? Then we need to know charge. The second equation we need to know is charge is equal to protons minus electrons. Remember, charge is always that little number at the top. If no charge is given, charge is 0. Again, if no charge is given, charge is 0. Atomic number equals the number of protons. Remember this, if no charge given, the charge is 0. So we have the charge is -2 for selenium. We have 34 protons minus electrons. So then we want to solve for E because we want to know how many electrons we need, because again, it's called electron configuration. So it's electrons. -2 minus 34, that's E equals -36, or E equals 36. So we need to house 36 electrons. We need to house 36 electrons. So what are we using? We're using the last sheet right here. And remember, we start all the way at the bottom and we build up. So the bottom is 1s. How many electrons fit there? 2. So this one's going to be 1s2. Actually, let me see if I can do something real quick. I want to put it right next to it. There you go. Okay. 1s2. Then the 2s. There's only one box. Remember, each box can only hold 2 electrons. That's 2s2. So we have 2, 4. Okay, and remember we want 36. Okay, we want 36. And after 2s, we have 2p. How many can we fit there? Well, we have 3 boxes, so that's 6. We can fit up to 6. So then that's 10 electrons there. Because remember, and what I'm counting there is I'm counting the exponents. I have 10 total. Right? Then after 2p, we have 3s. And then on again, we can only fit 2, so that's 12 total. 3s2. Then after 3s2, we have 3p. How many can we fit there? Well, there's 3 boxes, so that's 6, so that's 18. What's after 3p? We have 4s. We can fit up to 2 because it's only 1 box, so that's 20. What's after 4s? We have 3d. Okay, 3d, we can, and how many can we fit in 3d? Well, we have 5 boxes, 1, 2, 3, 4, 5. Each box can fit 2, so that's 10. So that's 30. What's after 3d? We have 4p. Okay, we're going straight to 4p. How many can we fit there? We can fit 6. We want 6 more, and that would give us our 36 total. So this is your electron configuration, or the long notation of Se minus 2. Questions on that one? Okay, so using your reference sheet, because you guys have access to the reference sheet, I want you guys to try number 3 by yourself, please. Try number 3 by yourself. Hey guys. So I just want to go through number 3. I'm sorry, I have my doctor on hold here. You know what, I'll call back. So let's look at number 3 real quick. F plus 1. So again, remember we have to look for the atomic number of F. F is number 9. Okay. So if its atomic number is 9, that's how many protons it has. So that means that the charge is equal to, and the charge, by the way, is given right there. It's -1. It's 9 minus electrons. So you subtract 9. Oh, it's +1, sorry. Subtract 9, subtract 9. So 1 minus 9 would give us -8. Is it +1? Yeah. It would give us -8 equals -E, or E equals 8. Right? So that means that, again, we use the last sheet. Our last reference sheet, and we start at the bottom. So we are going to start at 1s, and then we can put 2 there. So that's 2. Then we do 2s2. That's 4. Then we go to 2p. That's 3 of them that can fit there. Okay, so then, and then we need 4 more because we want 8 total. So our answer would be 1s2, 2s2, 2p4. Okay. Now let's do one with the noble gas configuration before we go. Number 5. It says give the noble gas electron configuration for S. So these are a little different. Remember, it's very similar to this still. We still need to know how many, electrons we're going to house. So first of all, we need the atomic number of S. So we're going to go to the first page. S is number 16, right? So the atomic number is 16. So that means he has 16 protons. Do we have a charge? The charge is no, we don't have a charge. So it's 0 is equal to 16 minus E. We subtract 16 to both sides. We get -16 equals -E, or 16 equals E. So we're housing 16 electrons. Now, what we're supposed to do here is we're supposed to look at the noble gases. What noble gas is close to 16 but doesn't surpass 16? Again, what noble gas is close to 16 yet doesn't surpass 16? Would it be neon or would it be argon? Neon, exactly. Neon doesn't surpass the 16, argon does. So what we would do here is we need to put neon in brackets. Now, neon, as you can see, it's number 10. So that means it's 10 electrons there. Okay. Neon has 10 electrons, meaning let's see where it leaves off here. So 1s is 2, 2s is 2, that's 4, 2p is 6, 8, 10. So that means that neon takes care of 1s2, 2s2, 2p6. So we just pick up where neon left off because we need to house 6 more. We need to go up to 16. Right? So after 2p, we have what? What's after 2p, guys? Where does the arrow point to after 2p? Anybody? Where does the arrow point to? 3s, yep. So we go to 3s and then we can house 2 there. So that's 12. After 3s, as you can see, it points to 3p. Remember, we want 16. So that would be, we just want 4, even though we know we can fit 6, but we just want 4 because that's how many, we need to house. All right, I want you guys to try number 6 before we leave, please. Try number 6. Okay, guys, let's go through number 6 just for time purposes. Give the noble gas electron configuration for Se. So remember, we have to find out what the atomic number of Se is. So Se should be somewhere here. Okay, what's the atomic number for Se? $34. Okay, so it's 34. No charge, that means it's 0 equals 34 minus E. Negative E equals negative 34, or E equals 34. Now let's look at our noble gases. Which noble gas is close to 34 but doesn't surpass 34? Argon. Yep. So we're going to put argon in brackets. And argon has 18 electrons. So then we're going to go all the way to the bottom again. We're going to see where argon leaves off. So 1s is 2. 2s is 2. That's 4. 2p, that's 2, 4, 6. That's 10. 3s is 12. 3p is 14, 16, 18. 4, 18. Okay. So 3p is 18. So basically argon takes care of 1s all the way to 3p. So we're going to pick up after 3p. What's after 3p? Where does 3p point to after it? After it. Does 3p point to 4p or where? 4s, exactly. 3p points to 4s. Okay. So we have 4s, and that would be 2, so that's 20. After 4s, where do we point to? Where does 4s point to after that? Yep, 3D. Okay, and then there we have 3D 10. We can house 10, so that would be 30. Okay. And then after 3D, where does 3D point after? 4p, yep. And remember, we just need 4 more, so that would be just 4. That way we have 34, and this would be our noble gas configuration. So remember, difference is in this one, we start at the beginning and we build our way up. In this one, we need to find a noble gas first that fits it, and then we pick up wherever the noble gas leaves off. All of these are obviously in your answer key. You have access to this in your answer key. So you guys can go back and check any of these out. You guys can obviously rewatch this video. I will upload it on YouTube. If anything, like I said, chapter 11, part 2, and then chapter 12, part 1, and chapter 12, part 2, I will be doing a video. If I don't get to do it live, I'm sorry about that, but yeah, that's just how whenever the baby comes, Okay. Questions? All right, guys, have a great day. I will see you guys hopefully Wednesday. If not, I'll see you guys next year. All right, bye-bye.